installed the BioC manager, you don't have to do these things again. You can only go with this one. Actually, we did this already with Reinhard. Reinhard showed you that there's bioconductor. So you have CRAN, which is a collection to work in R in all kinds of fields, from physics to chemistry, mathematics, and also biology. Bioconductor is specifically meant for tools to work on biodata. So everyone managed to get all these sequences for chymotrypsin and trypsin? Okay, so after we received all the different sequences, as you can see, they are stored in vectors, and each variable in the vector is a single character corresponding to an amino acid. This is not very convenient if I want to continue working like this, so we need to change it somehow. So the first thing that I do is I write it out as in faster format. And there is in second R, the library second R, there is a function called write faster. Okay? So what does it do? It takes in 3 different arguments. The first one is my sequences that I retrieved from Swissprot. Then I need to have the name for each of the sequence and where I want to write it to. So this is the file where I want to write it to. So check where you want to write it to, change to the directory where you want to, and then write a file. You should be in the directory MSA. So I write these 2 files. I will zoom out a bit so that I can see my working environment. So after I write these 2 files, if I look in the folder that I am in, I will have one file called chymotrypsin faster, and I will have one file called trypsin faster. Yeah? I can just look at them. It will open in R, and in a faster format, as we know, so we have the name indicated by a greater than sign, and then we have the actual sequence, followed by another name, followed by the other sequence, and so on and so forth. I will go back so that you can have a look at it. Okay, once you wrote those files, install the package MSA using bioconductor. Looking in CRAN, but we should look in bioconductor. These are the lines, the 3 lines that you see there. This is how you install it. Again, bioconductor is a collection of libraries specifically to analyze biological data. Everyone managed to install the library MSA? Yeah? Very good. So now let's continue. So MSA stands for multiple sequence alignment, as you already probably figured out. So we have a library in R that allows us to do multiple sequence alignments. You can also do it in other tools. There's Crustal W, there's Crustal Omega that will also do this for you. But since you are now R experts, you can just automate. Let's say you have 1,000 sequence where you want to run it on 20 sequence together and other 10 sequence. You can actually write your own script that will do it for you automatically. And then, now, we saved our data in faster format before because the library MSA needs it in faster format. It cannot retrieve the sequence in this list format where each variable inside the vector was isolated, so to speak. So first, we need to load the library. Now that we have installed the library, we load the library using the command library MSA. Yeah? Now, we read in the library, we read in the sequences that we stored before as faster format as with the function read AA string set. AA stands for amino acid. You can also read in DNA. You can also read RNA. So I encourage you to explore the library MSA. So if you go here into the right panel and you click on packages, once you installed it, it will appear here, MSA. So if I click on the link here, MSA, it will give me all the different functions that I have available in my library. Okay? So one of those functions is read a string set, and you will see. Anyway, so to read in a faster file, so we tell it, read in as the format is faster, read in a amino acid sequence, and this is the file that I want to read in. You remember the dot sign refers to your current directory. I like to use it just to make sure that I'm in the right directory. So I'm reading in the faster file that I wrote out before again, and I'm calling I'm assigning the sequences to two variables, chymotrypsin sequences and trypsin sequences. Okay? Okay. We will do the last thing for today. Okay. So I read into my variables. I'm looking at the variable, and you will see down here it would show me just a glimpse of it. So I have those 9 different variables. It will tell me the width of each variable in the first column. So the first variable has 276 different amino acids. And at the end, it would show me the beginning and the end of my sequence, and then it will tell me the name of the sequence that I assigned before. Yeah. Now, if I want to do this multiple sequence alignment using, I use the function called MSA. So all it needs by default are the sequences, and that's it. And it uses cluster W alignment. If you want to know exactly what cluster W does, in the lectures, in the presentation that I provided, you will find it. Okay? So I'm running my first alignment quite fast. I'm doing the same for trypsin, and now I have them aligned using cluster W. You follow? Downloading the library. Yeah, shoot. By the way, once you do the alignment, you see here a message: use default substitution matrix. What is this referring to? So I told you before, when you do an alignment of amino acid sequence of amino acids, you need to sometimes the substitution of an amino acid weighs in heavier and sometimes less. For instance, tryptophan, right? If it was conserved, it got a bigger score. So the default substitution matrix here is the BOSUM 62 matrix that I was mentioning before, and that you can also find in one of the presentations. Also for this kind of alignment, you need to have a substitution matrix. So how far are we? Who hasn't managed to install MSA yet? Who's still downloading? 1, 2. Okay, I see some of the people already. Yeah. Yeah. Okay. Once you do the alignment, look at the alignment, right? That's the first thing I will do. So I can look at it in a very simple manner. And it will show me here in my console how the different sequences align to each other. Okay? Doesn't really look nice. Okay? So you have the function MSA pretty print. What will it do? So this function pretty print will give you a PDF file. We'll call it chymotrypsin alignment.pdf. Then you ask me, where do you want to show the names of the sequences? On the left hand side. Where you want to show lower? On the top. Ask for override it. Do you want a message during while this file is produced? No, I don't want to see it. Do you want to show a legend? Yes, T for true. Okay? So this is the last thing that we will do for today. So if you execute now the pretty print, you will see that in your file environment, on the right hand side in your right lower panel, if you look at files, that a new file appeared called chymotrypsin alignment.pdf. Yeah? Here, this one. I see a PDF symbol, and I see my PDF that was produced by this line. If I click on it, it opens a PDF file. Okay? So on the left-hand side, I will have all the names of my variables, of my proteins, and then you will see that I have all the sequences aligned to each other. Now, what is the different color code? Yeah. So if I have a consensus sequence, which means, what is a consensus sequence? What? Conserve, right. Right. So I want to see whether I have amino acids that occur in all of my alignments. So if I have a conserved region, it will be highlighted in blue. That means that more than 50% of my sequences at this specific position have the same amino acid. And you can see the color code here. So if there is a green asterisk underneath your conserved region, that means greater than 50% but less than 75%. Hold on a second. No, the blue one, the turquoise one. The green one is, I think, greater than 75%. The yellow one is greater than 90%. And the red exclamation mark is 100%. I see I have a V in all of my sequences. Okay? Above my alignment, I will have this sort of annotation which shows you the conserved amino acid that you will have. So if you have all, here I have a D, I will have one big D that will tell me only this D occurs in all of my amino acid sequence and all my protein sequences. Here I have a P, and I have an N and a D. So it tells me in 50% I have a P, in less I have an N and only one D. Okay? So the size of the letters that are above my alignments represent the conservedness at this specific position.